Strategies to use in integration problems. The first one, look for something that's obvious. So try to find inside that integral, the integrand, that's the bit you're integrating, something where you see the derivative there as well. So can you get it to that idea of derivative times function, that sort of thing. Something like that. And you look at it and you go, hang on, actually, I see down here this function 1 minus x squared, but on the top of the fraction, I can create the derivative. So it's that idea we have seen in extension 1 of, can I create derivative times the function? Maybe that function's to some power, which in this case, the power would be negative a half. That then brings us to this one, to save yourself time. I would just know this. It's not on the reference sheet. It's one of what I call the non-standard integrals. Crops up so often in problems of that du on the square root of u. And the answer is 2 times the square root of u. Right? Because what would you have? You would have u to the negative half, add 1 to the power, it becomes positive a half, but it'll be 2 times it because it's power over that power of a half. So bang, you just go straight to 2 root u, save yourself some time. So I go straight to 2 root u, but the 2 times a half cancels, and I've got the answer. Minus the square root of 1 minus x squared. Can I manipulate it into one of our standard forms that we know? Okay? So we have our standard integrals. The whole point of those is to save you time. So once you've got your integrand and you've manipulated it into a standard form, you go bang, here's the answer. And that's like in that previous example, I'm saying, well, it's not on the sheet, but I have got it to a standard form. I know what du on root u is. So bang, I go straight to the answer. Now, of course, you might not see it straight away. How on earth do I turn this into a standard integral? And you can. A little bit of manipulation. You see, we've got e to the power of x plus e to the power of x. Using my index laws backwards, I can rewrite it as e to the power of x times e to the power of e to the power of x. Because remember, when we multiply, we add the powers. Well, I'm doing it the other way around. I'm saying, well, I've got add to the powers, so the same as multiplying. But now have a look at what we've got. We've got the derivative times e to the function, because the derivative of e to the x is e to the x. So that's the idea I'm using. That particular standard integral is what I've formed. So, okay, there's my answer. E to the power of x. What about this one? Wow, all sorts of things. But when I spot it, I notice the power of x on 2 and the power of x. Well, this x is double x on 2. So effectively, I could say, well, hang on, I've got a function squared here. That's the integral I've got. I've got derivative on a squared plus some function squared. All right, I've got to do a bit of manipulation to get it to what I want. So there's my manipulation. I'm saying the function is e to the power of x on 2. So this e to the power of x becomes the function squared. But hang on, my standard integral doesn't have 3 times the function squared. So I will factorize the 3 out, which now means on the bottom I have 2 plus the function squared. I want the derivative on the top. Well, the derivative of my function is a half e to the x on 2. So I need to balance that out. That means 4 also now needs to come to the front. But I now have 4/3 times a standard integral. I now have my answer. 4/3 times 1 over a in this case is the square root of 2. Inverse tan, that function, e to the x on 2, over a, the square root of 2. So I've got it, my answer, and just tidying that up, there it is, 2 root 2 on 3 times the inverse tan. Simplify the integrand, if possible. Again, algebraic manipulation, trig identities, these sorts of things can simplify integrals down. You look at this and you think, oh, I've got a function and the derivative as well, but unfortunately it's the opposite of what I'd like. Because this is function on the derivative, not derivative on the function. So something else is happening here. What's happening? I don't know. So let's use things that I do know. When it comes to trig identities, if I don't know anything else, I'll go, well, let's just change everything to sines and coses and let's see what happens. So the tan, I changed to sine on cos. Sec squared is the reciprocal of cos squared. Okay, now the cos theta will cancel with the cos squared, and I've just now got sine theta times cos theta, which I know is a half of sine 2 theta. And sine 2 theta I can integrate. Minus a quarter cos 2 theta is my answer. So that's a use of trig identities. algebraic manipulation. This is the really clever one. You got x cubed times the square root of 4 minus x squared. How on earth am I going to get that as derivative times function when the derivative is minus 2x? How do I turn x cubed into minus 2x? I mean, I can factorise out numbers from the integral, but I can't factorise x's out. I'm not allowed to do it. Right, so here's the ideas. We factorise by using the expression in the grouping symbol, which is 4 minus x squared. A multiple of its derivative, so minus 2x, or a combination of the both. That's what I turn it into. Minus x times 4 minus x squared plus 4x. What? Okay, so what have I done? I said I can't purely write it as derivative times function. Can't do it. So can I write it as a multiple of the function itself? And I can, because the x cubed I could rewrite as x times x squared. And that x squared then I'll make into the function, which is 4 minus x squared. But see, it was positive x cubed, so I need negative x out the front. So I still have the plus x cubed. But now I need to balance it out and add 4x on the other one. But what now happens is I have this. Because I've pulled out that 4 minus x squared, I don't have the problem of the x cubed anymore, because now both of these functions of 4 minus x squared to the power of something are times by x, and the derivative was minus 2x. So both of those I can now write as derivative times the function. Each one of these can now be done individually. Add 1 to the power over the power. There's the answer in all its glory. So algebraic manipulation's very clever if you spot it. You can save yourself a lot of time. But basically the idea is this. You look at the integrand and you will classify it according to the form of it, and then that will generally tell you the technique you're going to use. Rational functions. Some function of x over the other one. I don't know, x cubed plus 2 over x plus 1, whatever. Okay, polynomial division. That's a good way of doing it. And then a technique which we will look at known as partial fractions could help us with that. Trig functions. When we look at trig functions, the power of the trig function will tell us which technique to use. Again, we will look at a host of trig functions, how to approach them. It might be a mixture of function types. You might have an exponential with a trig function. You've got different types. It's probably going to be integration by parts, another technique that we'll look at. But at the end of the day, there's basically only 2 methods. Substitution and parts. One of those 2 things. Pretty much every question. One of those 2 things. So let's just start off playing with some strategies. So 4A and 4B, play with some of those.